Hello everyone. In this section, I will talk about the atomic orbital section. In the last three lectures, I have already discussed the basic concepts of atom and the quantum theory behind it. Here, I will talk about the atomic orbitals, how this atomic orbitals generates, and what is its physical significance. Now, atomic orbitals are mathematical functions that provide insight into the wave nature of electron that exist around the nuclei of atom. Generally, atomic orbital described in terms of three integral quantum number. We have already encountered the principal quantum number n, which has been derived from the Bohr model of hydrogen atom. Now, this principal quantum number, which is designated as small n, can have the integer value lying between the limit n greater than equal to 1 to less than equal to infinity. Now this allowed values of n arises when the radial part of the wave function is solved. So the Schrodinger equation consists of two parts. One is the radial part of the wave function and another is the angular part of the wave function. So when you solve the radial part, then the allowed values of this n quantum number, n, that is the principal quantum number, you can get. The two more quantum number L and ml appears when the angular part of the wave function is solved. Now the quantum number L is called orbital quantum number and has allowed values 0, 1, 2 to n minus 1. Depending on the value of n, the L can vary. L can have value 0 to n minus 1. Now the physical significance of L is that the orbital quantum number L determine the shape of the orbital, and it from the value of L one can determine the angular momentum of the electron by a formula that I will be talk about in later. Now the value of magnetic quantum number ml gives the information about directionality of the atomic orbital. So basically m is the magnetic quantum number, so it gives the directionality of the atomic orbital and has an integer value from plus L to minus L. So here you can see that the principal quantum number is designated in the symbol n. This is the principal quantum number and it can have values 1, 2, 3, the integer value. And what it signifies, or its physical significance, the orbital size, it gives the energy of the orbital. The energy you can calculate by this equation minus r into 1 upon n square, where n is the principal quantum number, r is the readback constant. Now L is the angular quantum number or orbital angular quantum number, which has a value 0, 1, 2 to up to n minus 1. It gives the orbital shape. So what kind of shape will be the orbital? It is circular or dumbbell shape, or the shape depend on this angular quantum number. Next is the magnetic quantum number, which values lies in between minus L to plus L. For example, if L is equal to 1, then ml will be minus 1, 0, plus 1. It gives the orbital orientation in space. Now cells and subcells. For n is equal to 1, so L value will be 0 and ml will be 0. Basically for n is equal to 1, L can have minus 1, 0 and plus 1. 0 for n is equal to 1, L can have only value of 0 because L can have the value up to n minus 1. So if it is n is equal to 1, so n minus 1 basically 0 and n will also be 0. So there is only one subcell. Basically this L actually designate the subcell. N is the cell and under its region, so there is one subcell, that is L, and that subcell has only one single orbital, that is ml is equal to 0. So basically, and that orbital is basically 1s orbital. So ml has a single value. So when you are saying ml has a single value, it means that it's for a single orbital, one orbital. This subcell is labeled S, and we call this orbital 1s orbital. So basically this set of quantum number 100, this set of quantum number is for 1s orbital. Now 1 is for this principal quantum number small n is equal to 1. When s is equal to s, for s the L value will be 0, and under this n is equal to 1, L is 0, there is only one orbital, single orbital, that has that value ml quantum number is equal to 0. Coming to the radial part of the wave function, how to plot the radial part of the wave function against small r, that is the distance from the nucleus, with the different orbital 1s, 2s, 2p, 3d, 3p orbital. Here I will discuss about that and its physical significance. Now the mathematical form of some of these wave function, the radial part of the wave function and the angular part of the wave function, are listed as shown over here. This atomic orbital, this 1s, 2s, 2px, 2pz, 2py, and their corresponding quantum number, radial part of the wave function and angular part of the wave function is given. Now this figure, this plot shows the graph between wave function, which is represented as capital R against the distance r from the nucleus for the different orbital as shown over here. Three representative figure here I have shown. One is, first one is the 1s, second is the 2s middle one, and second one is a combination of 2p, 3d, 3p and 4p orbital. Now, if you carefully look into the nature of this, all this graph, you will see that there is exponential decay with the distance. In every, for every orbital, there is a exponential decay with the increase in the distance. Now now check the first one. The for 1s orbital, capital R versus small r graph, you will see that it starts from it start from the y-axis and gradually decays, exponential decay, and it vanishes. So basically, if you see the 1s orbital corresponding radial part of the wave function, you will see that 2 e to the power minus r. So if you put the distance r is equal to 0, that is at the nucleus, so you will get a value like 2. So for the s orbital, 1s orbital, 2s orbital, it will always starts from this 0, r is equal to 0. Like here you will see that it start at x-axis, you look at it starts at x, r is equal to 0. So like from plus 2 to it gradually decays with increase in the distance r. Similarly for 2s orbital also you will see that it start at r is equal to 0. At r is equal to 0 it has some value, and it gradually exponential decays, changes its phase. There is one nodal point. Nodal point means there is probability of finding electron density is 0, and then again it exponentially increases and gradually merges to 0. So this is the nature how you can plot the 1s orbital and 2s orbital. Now for the 1s and 2s orbital, depending upon the node, nodal point, radial node, one can have the phase change. Like 1s orbital, you can see there is no node. Here there is no node. For 2s orbital, the second one in the middle, there is one radial node is there. So one radial node means there is one change of phase. So first it starts from like y-axis 0.75 and it gradually exponential decay. At r is equal to 0, it changes its phase, and then again it's gradually exponentially increasing. Like 2p, 3d, other all except for s orbital, all the other orbital, you will see that when you put r is equal to 0, the radial part is vanishes. So radial part is 0. So that means this kind of orbital, 2p, 3d orbital, it start from at r is equal to 0. There is no value at r is equal to 0. There is no y value. At y axis there is no value you will see. So it start from at r is equal to 0, and then it gradually increases, exponentially increases, gives a maxima, probability of finding electron density is maxima, then it gradually then exponential decay also. Similarly, for this kind of orbital, depending on the radial node that I will talk about in the later slide, how to calculate the radial node, it will change its phase. For like 2p orbital, there is no radial node. For 3p orbital, you can see there is one radial node. For 4p orbital, shown in the black in color, there is two radial node. At initially, you can see this is the first radial node, and second radial node is this second radial, two radial node, because two radial node means at x-axis it cuts twice. This 4p orbital, this radial distribution function plot at x-axis, it bisects twice. At initially at first you see near to like uh, uh, 2 value, and then at is equal to higher value of r with increasing distance of r. So this is the plot of the radial part of the wave function against distance. For a is equal to a, for a's orbital it always starts from r is equal to 0. Rest of the orbital it always starts at r is equal to 0. Like for a's orbital there is a definite value at r is equal to 0. For other orbital it will there is no value at r is equal to 0, and then it will gradually exponentially increase, and after a maxima it will exponentially decay and merges to 0. Now there are several point. Now there are several uh, point to be noted from the plots of this radial part of the wave function. So the A's orbital have a finite value of r at nucleus r is equal to 0. That I have already talked about. A's orbital at nucleus it has a finite value. That is why it at r is equal to 0, that is at nucleus, it always has some definite finite value, and it will not vanishes at nucleus. It will always have some value, and it will start from that value and exponentially decay. For all the other orbital except from s orbital, at r is equal to 0 at the nucleus, but capital R, that is radial part of the wave function, will be 0 at the nucleus. From the plot you will see that, like from the s orbital at the nucleus it has some finite value and it exponentially decay. For other than s orbital like 2p 3d, it always vanishes as r is equal to 0. So this point basically, this point basically r is equal to 0. This point basically r is equal to 0. Other orbital will like, so this will be the scenario. For 1s orbital, the radial part of the wave function is always positive. For the first orbital of the other type like 2p 3d 4p is r is positive everywhere except that the origin. Now the other orbital, basically depending on the radial node, the function will be positive in the first quadrant and it will be negative in the second quadrant. Now radial node can be calculated using this formula. In general formula, radial node can be calculated by n minus l minus 1. So this is the general formula. N minus l minus 1. You put the value of n, you put the value of l minus 1, you will get the radial node. Now for specific orbital, if you just include the value of l, you will get the radial node. For s orbital n minus 1, p orbital n minus 2, d orbital n minus 3, f orbital n minus 4. So depending on this radial node, so the value will be positive in one quadrant, value will be negative in other quadrant. For example, 1s orbital there is no radial node. For 2s orbital there is one radial node. So 2s orbital is positive in the first quadrant in the upper phase, and it will be negative in the it will it will sign the wave function will change its sign in the second quadrant. So you will see that by positive or negative, but the wave function has only one sign change, basically one sign change. So when some orbital has a radial node, so this is the radial node, this point is the radial node. So then you see this is positive and this is negative. The wave function will change its sign after the passing through radial node. The wave function will change its sign, and it will depend on the radial node. How many radial nodes are there in the wave function? Now you can calculate using this formula for specific orbital. Now coming to radial distribution function. Let us now consider how we might represent atomic orbitals in three-dimensional space. I have already told that a useful description of an electron in an atom is the probability of finding the electron in a given volume of space. So basically, the wave function psi, it has no physical significance or meaning, but the psi square, it has a meaningful significance. So that is that a probability of finding the electron in a given volume of space. The psi square has a meaning. It gives the probability function, probability distribution of finding the electron in a space. So by considering values of psi square at any point around the nucleus, we can define a surface boundary which encloses the volume of space in which the electron will spend, let's say, 95% of its time. This effectively gives us physical representation of an atomic orbital. So therefore, psi square may be described in terms of radial and angular component. You know that psi basically comprised of two parts. One is the radial part, one is the angular part. So therefore, the psi square also will be like r square, and this angular part this square. Now first we consider the radial component. So basically, a useful way of depicting the probability density is to plot a radial distribution function, and this allows to basically to understand the region of space in which the electron is found out. So basically, radial distribution function is given by this sort of form. Radial distribution function is given by 4 pi r square into radial distribution function square, 4 pi r square into capital R square, where r is the distance of this atomic orbital from the nucleus and capital R is the radial part of the wave function that I have told in the previous slide. So this gives a radial distribution function. Now how to plot this radial distribution function with the distance r from the nucleus? Now here the basic difference of plotting this function over the previous one, only radial wave function, is that here all the function will start from the value at r is equal to 0. All the function, s orbital, p orbital, d orbital, it always start from this r is equal to 0. In the previous example, I have said that for s orbital it will start from some finite value, it will not start from 0. But here all the orbital 1s, 2s, 2p all will start from at r is equal to 0. For 1s orbital this is like this, 2s orbital, 3s orbital, and here at the right hand side you can see the other type of orbital is given. How to plot them and how to analyze them, I will talk about this in this slide. So each function, that 1s, 2s, 3p, 3d, you can see over here, each function is 0 at the nucleus, following from the r square term, and the fact that it all start at r is equal to 0. Since this function depends on capital R squared, that is radial function squared, it is always positive in contrast to the radial wave function plot, for which you can see that you have already know that there is a positive quadrant and a negative quadrant, there is a phase change is also happening in that plot. But here all the plot will be in the positive part. There will be no negative value of the probability distribution function, because probability cannot have the negative value. Now each of this plot 4 pi r square into capital R square, each of this plot having some one maximum value. Here you can see the one maximum value, one maximum value, one maximum. Each of this plot, so at least one maximum value for the function corresponding to a distance from the nucleus at which the electron probability is highest. You can see that for 1s orbital there is 1, 2s orbital there is 2 maximum, 3s orbital you can see there is 3 maximum point. So this is the point where the probability of finding the electron is maximum. And those point where this value 4 pi r square into capital R square is 0, like in this point, these are called radial nodes where capital R is equal to 0. So basically points at which this radial distribution function vanishes, ignoring the R is equal to 0. It is This is the nucleus, except this point wherever you will find that this radial distribution function is getting 0, this is called radial nodes. Similarly, you can see that, for example, uh, 1s orbital, that radial node will be 0, so there is only one maxima. 2s orbital there will be two node. How can you can calculate? Similarly, n minus 1 formula for or I have already discussed. So there is one node, so basically you will get only one node and two maxima. 3s orbital there is two node, so basically you are getting two node, and the graph will look like this. There will be no phase change. All the function will be in the positive direction, positive value. All the probability part will be in the positive value. There is no function will come out the negative part, because you are taking the r square, capital R square, so there will be no negative value. Similarly, you can see that for 3D orbital, you can calculate the node 3 minus n minus l minus 1, n minus l minus 1. 3 minus l is equal to 2 minus 1, so basically 0. For you can see that 3D orbital there is no node, basically it starts from 0 and there is only one maxima at this point. This is the one maxima at this point. Similarly, for 3p 3s orbital, it all start from r is equal to 0, and depending upon the radial node, it will having this kind of 1 2 radial node, and all minimum at least one maximum value. And all these function, all these orbital, with the increasing value of r, it will exponentially decay and vanishes close to 0. The angular part of the wave function, it is given by this representation, capital A within bracket theta and phi. So there are two variables, theta and phi, and this angular part of the wave function, this kind of wave function, they are independent of principal quantum number. So basically principal quantum number will not dictate the this value, this parameter. For example, s orbital, the angular part of the wave function is given down over here, and you can see that from the value, it is just a value, constant number. For 1s orbital, this is the parameter orbital quantum number, n is equal to 0, principal quantum a is 0, ml 0. Radial part of the wave function I have already discussed, 2 e to the power minus r. Now here this is radial angular part of the function, this is nothing but a constant value. So you can see that for for s orbital, not one is, for any s orbital, this angular part of the wave function is like a constant value. It is independent of any principal quantum number or any theta and phi. You can see that angular quantum number, angular function, it actually is a function of theta and phi. But for s orbital, it is not depend on theta and phi. So basically it has a constant value. Thus, S orbital is spherically symmetrical in nature about the nucleus. You can see that this is the shape of the S orbital. Now, how come you can know the shape of the orbital? Shape of the orbital is originates from this angular part of the wave function. Angular part of the wave function, you can see that is spherical symmetric in nature. So it is not depend on the any theta and phi value. So this is the S orbital. This is S orbital, and this is spherically symmetric in nature about the nucleus. And the reason behind is that for the S orbital, the angular part of the wave function is not a function of theta and phi. It has a just constant. It has a just constant number of value. So at any point you will get the same probability distribution function. That is why you are getting a spherical function, spherical distribution shape for S orbital. Now for p orbital, you know that, let's say for n is equal to 2, so the value will be 0 and 1. 0 means it is s orbital. I have already discussed the same. It is spherical in nature. For l is equal to 1, it is p orbital. Now there are two type of orbital, two cell subcell. One is l is equal to 0, ml is equal to 0. This is a subcell that is basically 2s orbital. So this is basically nothing but 2s orbital, and there is another orbital L is equal to 1, and therefore there is 3 possibility. So basically 3 2p orbital. 2p orbital is known as, it has a 3 orientation directionality, and depend on these 3 directionality 3 ml value, it has a 3 orbital. Now this is a p subcell. So cell basically is that principal quantum number which is cell, and under that there is 3 p orbital, p subcell, and each p orbital, like p orbital with having 3 orbitals, that actually basically deciding the electron. So basically you can see that for p orbital, this is px, py, pz. So each of these orbital box actually can accommodate 2 electrons. So for p orbital there are 3 orbital naming px, py, pz, and each orbital can have 2 electrons. Now again, now the nature of the shape can be derived from that wave function equation, radial part and angular part. So if you taken care of this wave function, angular part of the wave function, radial part of the wave function, you will see that p orbital nature. So p orbital is like dumbbell like shape as shown over here. Depending on the axis it is oriented, it is can have px, py, pz value. So this is a typical p orbital nature, typical p orbital shape. uh, when L is equal to 1, there is a planar node through the nucleus. So basically this point, showing in the dotted line, so this point actually, this point showed that this p orbital having a node at the nucleus. This is a one phase, this is another phase. So here the electron is surrounded, is confined in this region, but in this region, in the plane xy plane, so there is no probability distribution of the electron. So it is 0. This is called node. Node. Now p orbital, like it has a 3 orientation depending upon that ml value. So plus 1, 0, minus 1. Now one of them will be px, py, pz. So basically the z for ml is equal to 0. This is taken care of the pz value, and rest of the two, one is px and one is py. Now for pz and px, py, you can see that the relative orientation, these three p orbital like 90 degrees apart from each other. You take any orbital, for example pz, so if this is the z direction, so and this is the xy plane, so this is the y and this is the xy plane, so this is the pz orbital, this is the pz orbital, so this is the pz orbital. and at the right 90 degree angle with respect to each other, right angle, you see that this is px, this is along x-axis in blue in color, and this is py showing in the green color. This is py, px and pz. These are three orbitals. So p orbital, you can see that px, py, pz, they are all dumbbell in shape, and their relative orientation, they are 90 degrees apart from each other in space. Similarly, d orbital, I have already discussed the number of possibility how to calculate the quantum number L, ml value, how to represent them. So basically, this example is given for n is equal to 3. You will know that there is three possible L values, 0, 1, 2. No, 0 means s orbital, this is 3s orbital, this is 3p orbital, this is 3d orbital. And so there are three subcells in the cell. This subcell is equal to this 3s, 3p and 3d in the cell. So this is one subcell, 3s. This is another subcell, 3p. And for the d orbital, you see that there are five possible value of ml value orientation. So there, that means that there are five orbital are possible. For d orbital, d subcell, which five orbital are possible. Now the values are given as dxy, dxz, dyz, dx square minus y square, and dz square. These are five d orbital. this is the quick recap of all the orbital I have talked about in this lecture. So these are the boundary surface for all orbital of principal quantum number n is equal to 1, 2, and 3 cell. Let's say for n is equal to for n is equal to 1 for n is equal to one subcell, one cell. For n is equal to one cell, for n is equal to 1, you can see that for n is equal to 1, so there is only one orbital, that is 1s orbital, which is basically spherically symmetric in nature, along the whole direction. For 2 n is equal to 2, for n is equal to 2, there are 4 orbitals are possible, 2s and 3p orbital, px, py, pz. For n is equal to 3, there are 9 orbitals are possible. One is 3s, there are 3p orbital of px, py, pz, and there are 5d orbital. There are 5d orbital. So total 9 orbital possible. So there are formula, there are tricks, number of orbital you can calculate for a particular cell given quantum number n. So basically n square. These are n square orbital of nth cell. So if the question is given for n is equal to 4, how many orbital are possible? N is equal to 4 cell, how many orbital are possible? So you can calculate that n square, that is 4 square, 16 orbital are possible. You can calculate all the possible orbital with the principal quantum of n, l, and ml. You will see that you will get 16 type of orbital, 16 different orbital. For n is equal to 3, you can also see over here. So there are 3 square, that is 9 orbital possible. So you can see over here 3 square, there are 9 orbital. For n is equal to 2, there are 4 orbital, that is 2 square. For n is equal to 1 square, 1 orbital are possible. So by calculating this number n square, you can have that number of orbital for n cell. Now for d orbital, you can see that there are 5 types of d orbital, naming dxy, dxz, and dyz. Now you can see that these 3 set of orbital, they are similar shape in nature and they are degenerate. These 3 orbital, 3 dxz, dyz, and dxz, they are called triply degenerate, and because of their symmetry, they are called T2G orbital. They are called T2G orbital, triply degenerate orbital basically. Uh, and another 2 type orbital, that is 3dz square and dx square minus y square. You can see that their shape is quite different from these 3 orbital, and these 2 orbital are called along with EG orbital, EG orbital. Now 3 z square orbital, you can see that the 2 lobes are there along the z axis. One is positive direction, one negative direction, and along the xy plane, this part which is given in the circular circle, this is basically radial. This is basically node. Here, this is the torus of electron density, and this is basically a radial node, 3z square. And EG orbital, you can see that the other orbital dx square and y square, along the x-axis or y-axis, the orbital are pointed out. So basically, d orbital, there are these 5 set of different orientation are possible.